In this video, we're going to explore the various commands for nodal distribution along an edge of a mesh, including RES, relative spacing by a ratio, AS, absolute spacing by the size of the first and the last elements, DRS, double relative spacing by two ratios, and DAS, double absolute spacing.
These four commands control how the nodes are distributed along an edge. Going back to this problem here, the assumption here was that the nodes are going to be equally spaced. But you may not want equally spaced. You may want to bias them so that they're clustered down here or up here. Whatever rule you want to invoke will cause the nodes to be distributed differently along this edge. And that's part of the algorithm that I'm talking about here when we talk about an edge being projected. There's another level of algorithm that moves them along this curve that's formed by the intersection of the two surfaces until they have been adjusted to satisfy one of these rules. So I'll explain what these rules are. So the RES command, you give it a ratio, in this case rho. And what it says is that for every node along this edge, the ratio of the distance between two consecutive edges of our mesh will form this ratio. In other words, delta sub I plus 1 divided by delta sub I is equal to our constant rho. Now, if you make rho 1, that means they're all equally spaced, and that's the default. But if you make rho small, that means that every edge is going to be smaller than the previous. So they get smaller and smaller as you know what that does is it causes them to cluster on this side and get very big on this side. Now, if you made rho large, let's say 10. By the way, that would be a ridiculous number, but let's just say take 10, for example. That is saying that every element is 10 times bigger than the previous one. So you would get some very large elements on this side and tiny elements over here. I would suggest you stay in the realm of 0.5 to 2. Anything bigger than that, and it's likely to cause numerical errors in your simulation. Now the AS command, we call this relative spacing, by the way, and we call this one absolute because it determines what rho is such that you can decide what the first element is or what the last element is. It determines rho in order to give you that size. And that's why we call it absolute, because you're giving it a specific length for the first or the last element. By first and last, I mean when you look at it from an index point of view. If this were an I edge, then the I would be smaller, the I index would be smaller here than here. So that is the direction where we could determine what is the first and what is the last interval. Now the DRS command, we have two ratios, one for the beginning part and one for the ending part. And in both cases, you give it a ratio, and it determines how big to make them at the beginning and at the end such that they meet in the middle smoothly. That's a well-posed problem. And the DAS is like the AS, but once again on both ends. You give the size of the first and the size of the last, and it determines the two ratios so that they meet in the middle smoothly. So those are the four methods that can be applied to the edge, the distribution of nodes, a biased distribution. And we're going to experiment with that along with things. And that's with this simple example. We're going to create a cylinder and a partial mesh projected to that cylinder. And then we're going to experiment with different commands, not only nodal distributions, which is part of the category of interpolation, but we're going to look at other interpolation issues, such as the nodes on the face, not just along the edges, but on the interior of the face. So here's what I'd like you to do now. Run this three lines of TrueGrid commands. The first one, of course, creates a block part. It'll be a shell because you can see the K index is a -1, and it's going to have two blocks in the I direction and two blocks in the J direction. These are the coordinates to get us to the desired result. We're going to create a cylinder, and it's going to be in the X direction. The axis of rotation is going to be the X axis, and it'll be a radius of 4. It's surface definition 1, a cylinder. The center of the cylinder is at the origin, 0, 0, 0. And the direction of the axis of symmetry is in the X direction, 1, 0, 0. And then the third command is the projection command. This is again the index progression version of it because it has an I as the last letter in the name of the command. And it's going to be the entire K face. So everything is going to get projected to our cylinder, surface 1. And that's what's spelled out right here, project to surface 1. I'm going to copy this, and I'm going to dump everything into that text window. I've got a mesh that's been projected to this cylinder. I'm going to put this in wireframe mode for graphics so I can see the mesh and the surface. And I think I'll get rid of the interior lines. That's the SDINT space off.
Our video called Environment Window Panels covers how to control the image in the environment window. If you are not yet familiar with the display commands, we suggest you watch this video and keep this page from our training guide handy as you learn to use TrueGrid.
First of all, if I go to the history window, the history window tells me that there's one command on this part, a projection command. I can turn it off and draw and show you what the mesh looks like before the Newton method is applied to it. Notice that it is not going through the center of the cylinder. That would be a disaster, because if it sat in the center, what's the closest point? They're all the same distance from the center. What random events would take place to have a node go one place or another? So we purposefully positioned it off of the center. Now I'm going to turn this command back on by clicking on the deactivated with the middle mouse button, and it reactivates it, and then tell it to redraw. Now what I'm going to do now is going to cement in your minds the order of events that take place. I'm going to move one of these vertices. So I'll go to Move Points, and I'll move in the screen plane. So I grab this vertex and move it over here. Well, it's still on the cylinder. TrueGrid threw away the entire mesh, started over, and it repositioned this particular vertex in a new location. Well, what was that location? Well, we can find out by once again going to history, turning off the projection so we can see what the projection sees before it actually does the projection. And that's what it looks like. And so it projects back to the cylinder. I'll turn the projection command back on. I can do this endlessly. I can move another guy over to here, move this one over to here. I can continue to do that. And always, every node of the mesh is on the cylinder, projected to closest point. But now I want to show you something that can go bad. So I move this vertex over here. I'm wrapping it around. And at some point, it's going to go spaghetti. There. But it has done exactly mathematically what it's supposed to do. Every node is on the cylinder. Even nodes that were starting out almost in the center, ended up going onto the cylinder. What has happened is there's too much curvature. You have to get the vertices close enough so that the curvature is not extreme. Well, in this case, I took this particular vertex and wrapped it around more than 180 degrees, so that the edge that came to that vertex started out wrapping around this way, but at some point it was shorter to go this way. And that teaches us a lesson that when you project to a surface of curvature, never try to get too many degrees of curvature between two vertices of your mesh. That means you may have to add additional partitions in the mesh and reposition them in order to capture all the curvature. Typically, we don't have that much curvature. I'm going to undo this. So now I'm back to where I was when I first started this. And I'm going to do some bizarre things to the mesh. I want you to see worst case scenario. You'll never get to this point to do this in any real problem, but it shows you when it's extreme just what can go wrong. So I'm going to use this edge right here and apply one of those commands that control the nodal distribution along an edge. I'm going to use the RES command, and I'm going to use a large number. Now, the commands that we're going to be using and have been using are all found under the Mesh menu. There are a few exceptions, but mostly this is our set of commands for building the mesh. And that may give you some relief, but it's still a large number. However, many of the commands are very similar. For example, these 4 commands are very similar. And when you understand one of these commands, how to use it, you'll understand all 4 of them. Okay, so now we're going to use the RES command on this. And now that I've selected the region, I've selected the command, I hit F1 to enter my selection. And you have to tell it which direction, which kind of edge this is. It's an I edge. And then we give it the relative spacing. Like I said, if it's 1, we're going to get equal spacing. I'm going to use 2. Way too extreme. When I say 2, it means that every element is twice as big as the previous. Well, let's test that out. Let's check it out, see if it's true. Now, one of the functions I told you about is the distance function. We're going to find the distance between 2 nodes. So I'll type this in. There are the coordinates, and I'll use the distance function under miscellaneous. Select that vertex or node and hit F7, prints the coordinates. Select that node, hit F7. And now I have that distance. Now I'll do this distance here. Select this node, hit F7, this node, F7. And now I have this second distance. I want to get their ratio, so I use the desk calculator, DC. And I use this number, so I cut and paste, divided by this number. And the number I get is 2.000029. And what we just did was calculate straight line. I was thinking that showed that there was an inaccuracy, but I'm not taking into consideration that this is on a curve. Now we're going to choose the opposite face and use a different command. This time I want to use the DRS command, which means I'll have 2 ratios, one for the left and one for the right. And I'm going to use 2 for both of them. So under Mesh, the DRS, I hit F1 to enter my selection, and it is an edge, again, in the I direction. And I'll use 2 for both of them. And that produced a very fine mesh on both ends and very large elements in the middle. Notice that this vertex, because we have 4 blocks here, this is a vertex. It hasn't been affected. We have not issued a command that affects this as yet. Well, except for the projection command. Now we're going to select this edge and use a third method for nodal distribution. It's going to be the AS command. And we're going to specify the length of the first element, and it'll determine the ratio in order to get a smooth transition. And this is now a J edge. So I hit F1 function key in the J direction, and I'll specify the first element to be 0.01. And I'll redraw the picture so it recalculates. But you would never do this in any real problem. And this is not a limitation of TrueGrid unable to make a good mesh. This is a constraint that mathematically has to be obeyed. Now the last one, this edge right here, we're going to use the DAS command. That is, we give it the size of the elements at both ends. Again, it's hit F1. It's a J edge, and I'll use 0.02 and 0.02. Now, I don't think that most engineers are going to use these biases to a great extent. For example, those that have, let's say, fine mesh on both ends, that is typically used in fluid dynamics, where you have 2 blades, one here and one here. So you want fine mesh for a boundary layer and then a coarse mesh in between. But for most finite element, you want a smooth, equally spaced set of elements. When you have a boundary and you have TrueGrid interpolate between the boundaries, it treats the boundaries as not movable. And that's what's happened here. For each one of our 4 edges, the end nodes were not changed. The end vertices are exactly what they were before these commands were issued. Now this intermediate one, this is also a vertex. It did change. Well, it may not have, but only out of coincidence. It is required that it follow the algorithm that distributes the nodes. So it is not movable. If I were to try to move that, you will see it'll still bounce right back. Because it no longer has any degrees of freedom, just like in finite elements. All of the degrees of freedom have been consumed by the constraint that says they have to follow that rule for nodal distribution. And the same is true for this vertex. And for this vertex, it doesn't even look like it's a vertex. It looks like it's got a triangle here, but in fact, it's not a triangle. If we go close enough, you'll see. But that vertex, which is quite close to the edge physically, is constrained to be there. So you can have these portions of the mesh that are completely consumed. Don't over-constrain something. So if I tried to project this or to apply another zoning rule to this vertex would be over-constrained, and TrueGrid would not be able to solve all of those constraints simultaneously. And it's hard to tell what you would get. Well, I'm going to show you an example of an over-constraint. I'm going to use equal zoning from here to here. That's this edge here, I think. So I'll use the RES command for equal zoning. I'll use a ratio of 1. And that's in the J direction, with 1 as the ratio from one element to another. So it's equal spacing. Well, it doesn't look so bad. Now I'm going to do the same for this edge. Then it's over-constrained. And who knows what it'll produce. Depends on when it stops iterating. Well, it doesn't look that bad. Okay, I'm going to make a mess. I'm going to undo that and use something different so that you can see what can go wrong. I'll use 0.1 as my ratio. There's no way all of those constraints can be obeyed at the same time. And as a result, the algorithm just keeps iterating, hoping to find the solution and never does. So you need to count constraints. When you project something, you're constraining it to a surface. That removes 1 degree of freedom. When you project it to a second surface, that removes a second degree of freedom. It only has one more, and if you apply a third one, you've consumed all degrees of freedom. Don't try to do anything else with that edge, because it will be over-constrained and the algorithm will not converge. That's why it's quite useful to use the history table to find a bug. Suppose you have a bug in your mesh. You don't know why. It's likely to be an over-constraint. So what you do is you select the part of the mesh that's giving you trouble. Let's say that was the problem. And then you do a history on that. And what you get are all of the commands that affected that vertex. And then you can start experimenting. Let's turn this one back on so it looks bad. So if we were to go to that vertex, click on it, and then do a history, we would see this. Now we can ignore 15 and 16 because they're already deactivated. So we only have two choices. Is it the projection or is it the RES command? Well, the easy thing to do is to turn off one of them and redraw. Voila, we found the bug.